So, welcome back to part 2 of our first lecture on nuclear materials. I hope you enjoyed your little coffee break. One of the nice things about virtual lectures is the opportunity to split things up into more manageable parts, so I hope it's been of some benefit to you. We left off in part 1 having reviewed the fundamental notations used, types of radiation, the derivation of half-life. However, so far we've only considered spontaneous decay. But when it comes to nuclear power, we can't simply rely on spontaneous decays. We must stimulate decay with the aid of neutrons. So how do we do that? How can we manage such reactions, and where do the neutrons come from? Well, first, we've got to consider how we categorize neutrons. And this is most commonly done in terms of their kinetic energy. As shown in this table in your notes, or not really a table, as shown, we can classify neutrons by their energy and often title these categories in terms of particle speed. So, for example, you've got slow or thermal neutrons are of an energy of around 0.003 to 0.4 electron volts, whereas fast neutrons are of 200 keV to 10 mega electron volts. Should you wish to consider a thermal neutron, that's the category I will most frequently refer to in the course, in terms of meters per second, if you'd rather, an energy of around 0.025 electron volts is equivalent to about 2,200 meters per second. So if you really want to talk in terms of meters per second, you are welcome to. I suggest you stick with electron volts. So how do we stimulate nuclear reactions with these neutrons? Well, let's get some terminology and notational points out of the way first. When we say nuclear reaction, what we mean is a process in which two nuclei, or one nucleus and a subatomic particle, such as a neutron, collide to produce one or more nuclides that are themselves different from the nuclide you started with. That means that a nuclear reaction always involves transmutation that change from one isotope to another. But it may also involve alpha particles, neutrons, protons, electrons, or positrons. And these sort of reactions were first studied by Ernest Rutherford, who you should know well at Cambridge. He was here. And it was discovered by him in 1919. And it was Rutherford that first transmuted an element into another by using alpha radiation to convert nitrogen into oxygen, as shown here in your notes. And this is how we present such a reaction. On the left-hand side, you have the target nuclide, in this case nitrogen-14. That absorbs an alpha particle, so we have the plus, the alpha, shown by helium, here again on the left-hand side. And it produces the product nucleus of oxygen-17 and hydrogen. You can alternatively, you can write such a reaction in a more compact form, as shown here, but this reaction is exactly the same. It's just another way of presenting it. And basically that reaction proves to Rutherford that hydrogen nuclei formed part of the nitrogen nuclei, and therefore could well be a fundamental building block of many other elements too, and perhaps even a new fundamental particle. And so he named it the proton in 1920. Now, such a reaction can have a threshold energy necessary for it to occur, should it be endothermic. Therefore, it could also have a Coulomb barrier, that being the energy needed to overcome the electrostatic repulsion of approaching positive charged nuclides. But such considerations aren't shown in the notations I've given you. Charges aren't considered in nuclear reaction equations, so that's something to think about. So, we've discovered a nuclear reaction and the notation for such reactions. Well, if we go back to neutrons now, how do neutrons react with matter? And what do we have to consider beyond simply if transmutation occurs? Well, neutrons can react with matter in several different ways. Let's first consider scattering, types of scattering. You've got elastic or inelastic. Elastic scattering refers to the collision between a neutron and a nucleus, where kinetic energy and momentum are both conserved. That means elastic scattering. Whereas for inelastic, only momentum is conserved, not kinetic energy. So the neutron loses kinetic energy and will then cause the emission of gamma rays, but momentum is conserved. And whether a neutron undergoes elastic or elastic scattering depends on a lot of factors, such as neutron speed and the cross-section of the nucleus, which is an important property that I'm going to cover in more detail at the end of this lecture. Okay, so neutrons scatter. However, that doesn't have any transmutation involved. It's not a nuclear reaction. So what governs whether transmutation actually occurs? Well, if a nucleus captures a neutron, a heavier nuclei will be formed, obviously. So such a change could make that nucleus unstable, and so it will become radioactive. That is neutron capture. A nucleus has absorbed a neutron and activated it, i.e. it's made it radioactive, so it's activated. One example of such activation is that of cobalt-59, which is a common alloying element, especially in stainless steels, which is a significant problem should it be in any of your materials you're going to put in your reactor, because you do not want cobalt-containing materials under radiation. And that's because, as shown in the reaction here, cobalt-60 is activated by absorbing a neutron, and it emits a gamma ray. And the product, cobalt-60, can then emit two further gamma rays and an electron to become nickel-60. Well, the problem of cobalt in nuclear materials is because cobalt has such a half-life of 5.3 years, it tends to stick around. And gamma rays are highly penetrating, meaning that if you've got cobalt in your materials, they're going to be very difficult to work with once they've been activated or irradiated, as they're going to harm workers in the proximity, because gamma rays are very harmful to biological material, and so you're not going to want to go near these. And as such, nuclear alloys have purposefully very low levels of cobalt, as cobalt is typically present in natural nickel deposits. Any stainless steel used in the nuclear industry doesn't just use natural nickel deposits, it has to use highly enriched or high purity nickel to avoid any cobalt contamination, because you don't want this cobalt-60 emitting your gamma rays and harming your people working, your personnel on your power plant. So that's neutrons leading to activation. Now let's look at neutrons leading to fission. Well, fission was discovered not too long after Rutherford's discovery. It was discovered by Otto Hahn in 1938, for which he received the Nobel Prize in 1944, with Lisa Meitner and her nephew Otto Frisch explaining it theoretically in 1939. And what they saw was a nucleus splitting into two lighter nuclei, i.e. fission. Now, such fissions can occur spontaneously, like I've said, without stimulation for very high atomic masses above 232. However, the rates of such reactions are so negligible that it isn't really feasible to use spontaneous fission for a nuclear reactor. What we do instead is we force fission by using incident neutrons. But it gets more complicated, because as a nucleus can undergo fission, it can only do so under certain conditions. For example, if a nucleus can undergo fission regardless of the incident neutron energy, we term that nucleus as fissile, or fissile rather. So if a nucleus can undergo fission regardless of the incident neutron energy or speed, the nucleus is termed fissile. If a nucleus can undergo fission, on the other hand, only within a threshold energy, the nucleus is termed fissionable. So there's a difference between fissile material and fissionable material. And here we need to greet our old friend uranium-235 once more, for uranium-235 is fissile, because as it absorbs a neutron, it forms the unstable uranium-236 isotope, then immediately splits into two smaller nuclei, which are then termed as fission fragments. So the daughter nuclei are fission fragments. They are the product of fission. And I say two smaller nuclei because there are numerous scenarios of product nuclei for uranium-235. So I can't explicitly say what isotopes, what elements will be created. And that's why I've given you some examples in the equations here in your notes, with the typical yield graph shown in the adjacent graph. So as you can see, there's a wide variety of fission products that you can produce from the splitting of uranium-235. And they are dependent on different situations. Now, I mentioned neutron energy and how thresholds may exist for the reaction to occur when we were talking about fissionable material. Well, further to that, a neutron will not always cause a fission if it passes through the nucleus. If you have a fissile material and you have a neutron, it won't always cause fission as it passes through the nucleus. For example, uranium-235 is much less likely to split if it comes into contact with a fast neutron than if it comes into contact with a very slow neutron. And that's because, if you think about it, you've got a uranium-235 nucleus and your slow neutron's very slow, so it spends more time within the nucleus of the uranium-235 than a fast neutron that only spends a fraction of the time within the nucleus. Okay, so it's much less likely to split under a fast neutron than a slow neutron, as the time spent inside the nucleus decreases as the speed of the neutron increases. Therefore, with less time inside the nucleus, there's less chance of causing a fission event. Not only that, but if we're to produce a power plant that runs with sustained power production, these sort of reactions have to occur repeatedly and in a controlled manner. And so you can see where I'm going with this. We have to produce a sustained reaction, which we term a chain reaction. So we need to produce a chain reaction. And each fission event that we create has to produce more than one neutron. Every event you split has to produce more than one neutron in order to create this chain event. Fortunately, uranium-235 produces an average of about 2.4 neutrons and releases about 200 megaelectron volts of energy, 35% of which we manage to successfully convert to electrical energy in a modern power station. So, we've got this fission. It produces around 2.4 neutrons per event. Well, the products, or the fission products, will themselves decay as well in what's known as a decay series, which is what you can see at the bottom of this page here. This is the decay series that ends up with zirconium-94. So all these reactions are occurring in huge numbers constantly across the reactor core during operation. And these must be managed to ensure a safe chain reaction can be sustained. And a key term in this endeavour is neutron economy. And I'll talk in detail later on about neutron economy when we're talking about moderators. Because neutrons can be lost in a lot of ways. It can be lost to fission itself that we want. It can be to non-fission capture by the fuel. Like I said, sometimes a neutron will not cause fission, but sometimes it will be captured, but it won't cause fission. Or the neutron can just go through the fuel, miss everything, and end up being absorbed by another component, like the cladding that holds the fuel, encases the fuel. Or it can go past the cladding and just leak out of the core entirely. So there are many ways that neutrons can be lost. And on that point, a good way of thinking about it is you may have heard of something called critical mass. Well, what is critical mass? Well, critical mass is where you have it's a minimum size for a sustained chain reacting system, i.e. where the product of neutrons by fission balances the loss of neutrons to those other processes like capture without fission or leaking. So that means that a chain reaction can occur when the product of neutrons balances the loss of neutrons. That's when you get your chain reaction. So what else can you get? Well, should more neutrons be lost than produced, you're going to have a subcritical system. Should you produce more than you lose, you're going to have a supercritical system. And a supercritical system is not what you want. That results in a runaway reaction, leading to what occurs during the detonation of a nuclear bomb. Subcritical, our reaction won't be sustained and will die immediately, and so it's pretty useless. So evidently, reactor design itself holds a lot of challenges in its physics alone, and probability plays a key role in producing a sustainable system. And the probability of reactions is typically defined in terms of something called cross-section. Now, this might seem a bit confusing, but the cross-section of a reaction is what I'm talking about, and the cross-section of a reaction defines the likelihood of a reaction. The higher the cross-section, the higher the likelihood of a reaction. Should something have a high cross-section, it has a high probability that it will occur. And it's termed cross-section because it's roughly the projected area of the target nuclide, and is usually denoted in units of barns, where 1 barn is equivalent to 10 to the minus 28 meters squared. So using such cross-sections, we can model or estimate the reaction rates in a nuclear reactor. All you need is the neutron flux, i.e. the number of neutrons travelling through a unit area per unit time, and the cross-sections, i.e. the likelihood those neutrons will cause a specific reaction. So to design a reactor, you have to know all the cross-sections for all possible reactions for all present nuclei, all of which are energy dependent and will change over the reactor lifetime. So it's a pretty big job, as you can see. So we've talked mostly about fission cross-section now, but which is the probability to cause a fission event. However, there's also a scattering cross-section for the likelihood of, you guessed it, scattering. And finally, a capture cross-section. And the capture cross-section describes the likelihood of capture without fission. And all of these are a function of energy, like I said. And in the graph I've given you in your notes, although mine is sort of across the bottom of the page, these are readily available online for all your different elements. This one is for uranium-235. It describes the likelihood of these different events happening as a function of energy on the x-axis. So your barns are on the y, your energy on the x in a typical cross-section diagram, and it shows how the likelihood changes as a function of neutron energy. And for this one, you can see that the likelihood of fission goes down in general with increasing neutron energy. So that's why in thermal reactors we slow these neutrons down. We like to have them thermal, so there's going to be a higher probability that they're going to cause a fission event. And in the table that I've given you here, you can see I've provided a number of examples of the cross-sections for fission and also absorption, followed by gamma ray emission. So you've got fission in one column and absorption followed by gamma ray emission. They're the different cross-sections, shown as sigma. This typically denotes cross-section. And adjacent to those values, you'll see binding energy and fission barrier. In order for fission to occur, the binding energy of your incoming neutron to the fissile nuclide, the binding energy must exceed the energy necessary to split it. and the energy necessary to split it is termed the fission barrier. Should the fission barrier be greater than the binding energy, it will not fission. As we can see, let's look at thorium-232 there in comparison to the fissile uranium-235. Thorium-232, the fission barrier is greater than the binding energy, so it's not going to fission. And really, that is nuclear fission in a nutshell. In the next lecture, we'll cover fusion, and then we'll go on to nuclear reactor design, so how we use these fundamentals that we've covered in our first lecture as we start our journey from the design of the fuel itself out to the components beyond and outside the core. Now, it's quite a lot for a lot of you that haven't had a nuclear engineering education before this, or haven't done much physics. It's highly likely that you'll need to refer back to this section in that case, to this section of the course, as a lot of the terminology and notation will be new to you. So, don't be disheartened should you find yourself confusing certain terms in the early days of the course. You'll be speaking nuclear lingo in no time. Okay. So that's lecture 1. Again, should you have any questions, please feel free to comment, and I will do my best to give you a speedy response. And I'll see you next time.